Welcome to another lecture. In this video lecture, I will discuss about the non-competitive inhibition. In the last video, I discussed about the competitive inhibition, where we have seen that the inhibitor binds to the active site of the enzyme, where it change its the enzymatic the structural conformation of the enzyme. So as a result of that, the substrate cannot bind to the active site of the enzyme, so no product will be formed. But in the case of non-competitive inhibition, the inhibitor will bind to the enzyme's active site, as well as it can also bind to the enzyme substrate complex. Okay, so let's start with the normal enzymatic reaction. There is a enzyme binds with the substrate and convert it to enzyme substrate complex. Okay, and after that the substrate will be converted into the product, and enzyme will be released as a free enzyme, right? Now if we add the inhibitor in this system, if we add inhibitor, as I told that in the non-competitive inhibition, the inhibitor can bind with both the enzyme and as well as with the enzyme substrate complex. So here the enzyme is added, and also inhibitor is added, and here also the inhibitor can bind. Okay, now after that what will be happen here? The complex will be enzyme inhibitor complex, and in this case the complex will be enzyme substrate inhibitor complex. Okay, in that case the enzyme substrate inhibitor complex, and this complex is known as the ternary complex. Okay, ternary complex. So once the ternary complex is formed by the inhibitor, we cannot get any kind of product from the enzymatic reaction. The only way to get the product is when we have the enzyme substrate complex only. Okay, and if we see this kind of reaction in different reaction center, in the reaction medium, then we can see a particular phenomenon that I will show you. First I will tell you the normal enzymatic reaction, okay, with two type of graphs. So this is the direct plot, so let me write it here. This is the direct plot, where we can depict the graph of the Michaelis-Menten equation, and this one is the double reciprocal plot. This is the double reciprocal plot, or it is also known as the Line-Weber-Burke plot. Okay, now this axis, this y-axis is indicating the velocity of the reaction, right? And this x-axis is indicating the concentration of the substrate. Now if we see the normal enzymatic reaction, so this particular reaction medium is represented as the normal reaction enzymatic reaction, where previously these black dots are the enzymes. There are 6 enzymes that are given to the system or to the reaction center from the initial time. Okay, and these blue color dots are the substrate. So substrate concentration are huge in compared to the enzyme. Now what will be happen in this stage? At the middle stage, we can see that only 3 dots are saturated with the blue dots, that means, or attached with the blue dots, that means the 3 enzymes out of 6 are saturated with the substrate. Okay, and here all the enzymes are saturated with the substrate. Substrates. Okay, now after that some free remaining substrates will also be there. These are the remaining free substrate. So there are no enzymes, so that it cannot this substrate cannot bind to the enzyme. So these are free substrates. Now if we want to depict this kind of reaction in the graph, then we can see such kind of hyperbolic curve in the direct plot. Okay, this kind of hyperbolic curve in the direct plot. Here this particular point this particular point is indicating the maximum velocity of the reaction, and this particular situation is representation of this final stage or this particular stage of the reaction where all the enzymes are saturated. That means the reaction is gets its maximum velocity. So this is the region where the reaction achieves its maximum velocity, or this particular situation, this particular stage is represented in the graph at this particular position. This position is known as the V max, that is the maximum velocity. Okay, and here and this graph is this graph is the representation where no inhibitor is present. Okay, only the normal reaction center. Now the same thing, okay, let me tell you another thing. So this will be the, so assume that this particular point will be the at the y, along the y-axis is representing as the V max. V max, okay, and if you assume that this particular point or this particular line is the half of the total velocity or maximum velocity, then it will be the V max. This is the initial velocity, and this will be the V max by 2. Okay, so this is the half of the reaction, and if we plot, if we just draw the line, horizontal line with this graph, and where it is connected here, from here we can draw the vertical line. I don't know whether it is straight or not. Okay, whatever it may be. Now this line is, this point is connected with this point on the y-axis. So this is representing the Km of the reaction. So which stage of the reaction is indicating the Km? Now you can see by looking at the middle stage here, out of 6 enzymes, only 3 enzymes are saturated with the substrate. So this particular 3 substrates are the concentration of the substrate where the reaction has achieved to reach half of its maximum velocity. Means half of the enzymes are now free and half are saturated with the substrate, and that substrate are that concentration of the substrate are actually responsible for making the reaction to reach its half of its maximum velocity. So this 1 to 3 enzymes are representing the concentration of the substrate, that are the Km. Okay, so that concentration is represented here as a Km. Now if we want to depict the same thing with another plot, then we can see such kind of line. We can see such kind of line. Okay, now so let me draw it little bit from below, otherwise we cannot draw another line. Okay, okay, so you see this particular vertical axis is actually representing the 1y v0, that is the initial velocity, and this axis is indicating the 1 by substrate concentration, and here minus 1 by Km. Now the intercepting point of this line is indicating the 1 by V max, that is the maximum velocity of the reaction, represented in the double reciprocal plot that we cannot see in the direct plot or Michaelis-Menten plot. Okay. Now here the slope will be then Km by V max. Now I am not telling all these things. Okay, but because I have already uploaded one video regarding to that Lineweaver-Buck plot. Okay, and here this particular connection, this particular point where it is connected in this direction is indicating the minus 1 by Km, that is the Km concentrate or Km value of the reaction. So this is for the normal reaction. Excuse me. So what will be happened if we add the substrate, if we add inhibitor in the medium? So let's say we are adding inhibitor in the same situation, in the same reaction. So what will be happened? Substrate will be here, okay, the substrates are there, these blue dots are the substrate, and these are the black dots are the enzymes. Now suppose if we add inhibitor, then as I told, inhibitor can bind to the enzyme, as well as it can also bind to the enzyme substrate complex. So let's say this particular one enzyme is bound with inhibitor. So here no enzyme, no substrate can bind with the enzyme, and this particular enzyme is having the substrate, this one is having the substrate, and this one is having the substrate. Okay, only one inhibitor is bound with the enzyme. So no enzyme substrate complex can be formed here. So in this, so this is one stage. In another stage, what will be happened? In another stage, what will be happened? This inhibitor can be dissociated, because this is the loose connection or the non-covalent interaction between the inhibitor and enzyme. So after a certain period of time, the inhibitor can easily be dissociated from the enzyme, right? Now it will be dissociated, and enzyme substrate complex can form later on. Okay, and here previously it was added here. Now what about this two one? This one and this one. So once the enzyme substrate, because this is the period of making the conformational bond, okay, means the bonding very much fitting, the bonding will be very much fitted, okay, or very rigid. Now in this situation where I am talking about this particular two enzyme substrate complex, not with this one. Now here, as the enzyme substrates are formed here, the complexes are formed here, also the inhibitor can bind. The inhibitor can bind, okay, and the rest of the enzymes are saturated with enzymes. Sorry, it should be blue, sorry. Should be blue, okay. Now from here we can get the product only from this one, this one, this one, and this one. So four product we can get. But if we allow the reaction to retain up for some time, some time, then it will give the total, but it will take too much time. Okay, but up to this stage we can see that out of 6 enzymes, only 2 are, all are saturated with the substrate, but due to the binding of this inhibitor with these 2 enzyme inhibitor complex, all the enzymes or all the enzyme substrate complex cannot be transformed into the product. Okay, means all the substrate cannot be transformed into the product. So here only 4 products we are getting. That means the maximum velocity here it is not achieving. Okay, it is little bit lower in compared to this one. Means the efficiency of the enzyme or enzymatic activity will be decreased. Okay. Now in that case, what will be happen if we look at the graph? So here first I'm telling about this stage. Though the inhibitor is bound with the enzyme, but 1 to 3 enzymes are bound with the substrate. So here no changes in the Km. So 3 substrates are actually making the reaction to reach half of its maximum velocity. So here no Km is changed. So due to the binding of this inhibitor at the enzyme substrate complex form, the product formation will be reduced, or the enzymes cannot produce or cannot make the substrate to product. Okay, now if we want to see that kind of situation in the graph, then it will be So this is uninhibited reaction. This is what this line is for, the uninhibited reaction, and this is also the inhibited reaction. Now for the inhibited reaction, if we add inhibitor, you see the Vmax is now reduced. So it will be connected somewhere here. Okay, so it will be connected somewhere here. So somewhere it is, this particular line is a V max for the inhibited reaction. Okay, when we add the inhibitor in the medium, and this one is the half of the V max. This is the V max by 2 for this inhibited reaction. Then now you see the Km remains same, so that will be the Km prime. So here the Km is not getting changed due to the less efficiency of the enzymatic activity. We are having the less amount of product, so not all the enzymes are saturated at the final stage. Okay, though it is they are saturated but not able to produce the product due to the binding of this inhibitor on the complexes. Okay, enzyme substrate complexes. Only the free enzyme substrate complex will give the product. So this one will give the product, this particular, and this inhibitor bound enzyme substrate complex are the ternary complex, from where we cannot get any product. Now if we want to see such kind of inhibition in the direct plot, in the double reciprocal plot, then we can see such kind of, so Km will not changed, but you see the V max is getting decreased. So the line will always be above to this normal line. Now this one will be the 1 by V max prime. This is the 1 by V max prime. Okay, and here the Km will not change. Okay, now for this reaction we can understand, or we can have the equation for initial velocity is equal to V max into the concentration of the substrate divided by Km, alpha Km plus alpha substrate concentration, alpha prime substrate concentration, and this alpha is equal to, I also told in the previous video that alpha is equal to 1 plus concentration of the inhibitor divided by equilibrium constant, association or dissociation equilibrium constant or constant. Okay, now this particular, this is the uppercase K. Okay, Ki. Now Ki is equal to, also the Ki is equal to enzyme inhibitor concentration divided by enzyme substrate inhibitor complex. Okay, so let me check it once. Okay, whether okay, okay, this one, this is the equation for this non-competitive inhibition. And for example, in the daily life we can say that in the brain, As we know, in the glycolytic pathway, the glucose is actually phosphorylated by the hexokinase, where if it is present in the muscle cell, and it is phosphorylated by the glucokinase when it is the glycolysis is occurred in the liver cell. So whatever enzyme it may be, basically it will form the glucose 6 phosphate. Glucose 6 phosphate. Another intermediate from that will be the fructose 6 phosphate. Fructose 6 phosphate. Okay, so it is coming from the glucose with different enzymes. So once the fructose 6 phosphate is formed, now to regulate that, what will be happen? This fructose 6 phosphate will bind to the hexokinase. And due to the binding of this fructose 6 phosphate with the hexokinase, now the hexokinase is not able to phosphorylate this glucose into the glucose 6 phosphate. So this is the one example. You can find many examples if you go through the internet and Wikipedia. So this is all about the non-competitive inhibition, and in the future video I will discuss about the uncompetitive inhibition. Okay, and I hope I have not missed in this lecture. Okay, and if you find anything wrong, then please give in the comment box. Okay, and so that's it, and I hope it will help you a lot. So thank you, and subscribe my channel and like it and share it to your friends. Okay, so thank you.